We begin this video with an example that illustrates the methods that were mentioned at the end of the last video. We consider the sequence an given by n squared divided by 3 to the n, and we want to determine if this sequence converges, and if it does, we want to find its limit. We may begin by checking what happens with the sequence when n approaches infinity. Well, this is what we want to find out, but we may check that the numerator approaches infinity and so does the denominator. So we don't know what happens. So we need to try something else and just basic rules to figure this out. We may notice, well, we want to use the fact that if we consider the function f of x to be x squared divided by 3 to the power of x, then we are in the case that the function restricted to the natural numbers is the sequence we are considering. And the advantage of doing this is that then for this function we can apply L'Hopital's rule. So we have in the numerator we have the function x squared, which is a nice smooth function. In the denominator we have also 3 to the x is also differential, and then each of them, as x approaches infinity, they approach infinity, and we are considering the quotient of them. So by L'Hopital's theorem, the limit at x approaches infinity of x squared over 3 to the x is the same as the limit as x approaches infinity of the derivative of x squared, which is 2x, divided by the derivative of 3 to the x, which is logarithm of 3 times 3 to the x. So this is what we get from applying L'Hopital, but if we check now, we still have the problem that the numerator approaches infinity, and so does the denominator. So we can apply L'Hopital again. Again, the conditions for L'Hopital are verified because in the numerator we have a polynomial. Well, now we just have a linear expression, and in the denominator we have 3 to the power of x multiplied by a constant, so this is also differential. So by applying L'Hopital again, this is going to be the same as the limit when x approaches infinity of 2 over, where we are going to have the logarithm of 3 squared now, and then times 3 to the power of x. Now the numerator is constant and the denominator is approaching infinity. So we can conclude that this limit is 0. But then if we know that the limit of the function is 0, then the limit of the sequence is also 0. So the limit of an as n approaches infinity is 0. And we showed that the sequence converges and its limit is 0. Another very useful tool for finding limits of sequences is what we call the squeeze theorem. The situation is the following. Let an, bn, and cn be 3 sequences such that an is less or equal than bn is less or equal than cn. So the terms of an are less or equal than the terms of b, and which are less or equal than the terms of c. And this, well, we don't need this to be true for all the terms of the sequence, but we need it to be true for all n greater or equal than some capital N for some n. So after some point, the terms of the sequence B are sandwiched between the terms of sequence A and the terms of sequence C. If the limit when n approaches infinity of the sequence an is equal to L, and so is the limit when n approaches infinity of the terms of the sequence Cn, then the sequence Bn, which is in the middle between an and Cn, has no other option but to also have limit L. So the limit of the limit of the sequence Bn as n approaches infinity is equal to L as well. A picture is going to be very useful here. So let's say we have some limit L. So let me draw a line with L. So here's our L. And then let's say I'm going to use different colors. Let's say we have here the terms of the sequence. This with red is, sorry, I started writing A, but I actually mean this is the terms of the sequence Cn. So I don't know what they do for a while, but then after a while they approach the value L. With a different color, I'm going to draw the terms of the sequence AN. So this is A1, and then we have A2 and A3 and so on. And as n approaches infinity, the terms of this sequence also approach L. Now, the sequence Bn is in between the purple one and the red one. So I don't know, here there's one term, then there's another one. So they are there. But as n approaches infinity, they have no other choice approaching L as well, since the other two sequences do. Let's see an example of how we apply this theorem. So let's say we want to see what happens with the sequence cosine of n divided by n for n greater or equal than 1. So we want to classify the sequence, we want to see if it's convergent, and if it's convergent, we want to find its limit. So we may want to observe that the value of cosine is always between -1 and 1. So if we divide by n for any here, and we need to make sure it's greater or equal than 1, then we're going to have the chain of inequalities that -1 over n is less or equal than cosine of n over n, which is less or equal than 1 over n. Now, we know what happens as n approaches infinity with the smallest sequence and the biggest sequence over here. We know that they both approach 0 as n approaches infinity. So, by the squeeze theorem, because we sandwich the sequence cosine of n or n between the two of them, then we conclude that this limit is also 0 as n approaches infinity. And I leave here one more example for you to practice. So again, decide whether the sequence converges or not, and if it converges, find the limit. And in this case, the sequence is going to be given by -1 to the power of n divided by n factorial for natural numbers n. So try to apply the squeeze theorem to see what's happening with that sequence. As a corollary of the squeeze theorem, we have the absolute value theorem. So corollary means this is as a consequence of the squeeze theorem, we can prove this new theorem with very little work. So if we have a sequence an, and we know that the limit as n approaches infinity of the absolute value of an, so the new sequence that is the terms an but now with the absolute value, if we know that this limit is 0, then the limit of the original sequence as n approaches infinity also has to be 0. So I won't write what the proof of this is, but I'll just let you know what you have to do, and you should try. So try to apply the squeeze theorem for the sequences minus absolute value of an, and absolute value of an. Another tool we are going to need is the behavior of the geometric sequence r to the power of n. So we want to see what happens as n approaches infinity with this sequence, and well, this depends on what kind of value for r we are considering. For instance, if we are considering a value for r that is less than -1, I don't know, for instance, let's say -2, then as we consider consecutive terms, we're going to have -2, 4, -8, 16. So what's going to be happening is that in absolute value, the terms of the sequence are going to be getting bigger and bigger, so approaching infinity, we can say. But they also are going to be alternating sign. So the sequence is oscillating and getting the terms getting in absolute value are getting bigger and bigger. So this limit does not exist. Similar is the situation when r is equal to -1. So then the sequence is going to be -1, 1, -1, 1, and so on. It's oscillating between the values of -1 and 1. So again, the limit of this sequence does not exist. If the value of r is in absolute value less than 1, so we are considering all the values between -1 and 1, not including the endpoints, then we know that the limit of this sequence is 0. Even if the terms are oscillating, in the case of a negative r, they are in absolute value approaching 0, so it converges to 0. If r is exactly the value 1, then the function is the constant function 1, so the limit is 1. And if r is greater than 1, then the terms of the sequence are getting bigger and bigger, so we can say that diverges to plus infinity. So we're going to see very soon that the behavior of the terms of this special case of the geometric sequence is going to be very useful.